So the next step is let's look at the genetic map and qualify it. And Alex Kozik has come up with a nice program called Check Matrix, and it's available at the NavMapper site, the same site that we started with. And it needs 3 sets of files. The pairwise distance file, which we generated in NavMapper when we were doing the groups. It needs basically the order of the markers from, and not even the distances, just the order in this case from record. And I say reformatted. Basically all we've done to reformat it is we've grabbed the marker names, the orders, and we've added a column with the linkage group number here on the side. Right? And so we've added one more column with the linkage group number. So you can collate all your linkage groups to run through Check Matrix. And then the loc file, the same one that you put in the input record to start with for your linkage groups. Then you run Check Matrix. So Check Matrix, again, you have a Python script. So you call the program up using this this script here, basically PyMatrix, and you call up the pairs file from NavMapper. You call out the order file, which we just exported from record, and you tell it the name of your output file. The X and the Y, in this case, are just basically dummy variables where if you do have a framework marker list, you would put the name of that file with the framework marker list. If you actually have a list of markers that you want to highlight in red, or basically highlight, in this case it's going to come out in red, for any reason. They could be key anchor markers, they could be markers for traits that you're interested in. It really doesn't matter. Any markers that you want to list in red. Your input file, basically your for your linkage group. And then basically, do you want the graph to be displayed based on recombination, bit scores, or LOD scores? If you go down here, those are the different options. So you could put rec, bit, or LOD here. Check Matrix can put out a type of graph. It's really a circular graph that it's like a network graph between all markers, which we don't use generally, so we just put in the option no graph in this case, but you can put graph or no graph. This is the maximum recombination or the linkage cutoff. We just put this at a maximum of 0.9 because we already have done this in our grouping in our record analyses. Okay, so we just say include all the markers. We don't really want it to be filtering our markers at this point because Check Matrix is really a visualization tool as opposed to a mapping tool per se. Small, you can put small or large. This is the size of pixels, and you'll see what I mean when I show what the Check Matrix displays look like. It's really the size of pixels you want to see in your display. We use small. If you have a lot of markers, you would probably want it small as well. And again, the population type. And again, all this is explained in the README file for Check Matrix once you click onto the line, online to it. The next thing you want to do is to look at your file on either your PC or your Mac to display it, and you have to be able to grab that file from your new Unix system, and bring it to your computer, bring it either to your PC or to your Mac. And there's different programs that you can use. One is WinSCP. Here's the download for it. And what it does, it basically opens a window and basically allows you to see the directories and the files you have on your Unix system here, in this case on the right, and the files on your computer on the right. And you can basically drag and drop the files you want. The file you want, so you find your Check Matrix folder, are the PNG files. And those are basically the files or the diagrams that Check Matrix puts out to let you look at your maps. And this is exactly what you see for Check Matrix for a single group. And there's a lot of information here which allows you to see thousands of markers in one look. So what you want to, basically what Check Matrix is doing is aligning all markers by all markers. And it's asking the question, are they genetically linked? And basically what you want to see is a nice red line down the middle over here. So basically red means high linkage, strong linkage, and blue means negative linkage. You really don't want to see blue within the linkage group because it means there's some markers that really are in repulsion to other markers within that linkage group. And the yellow, and basically, it's grades of color from basically red to blue. So there's a number of things you see here, although it can be fuzzy. So the areas where that have large spots, I mean there's a lot of markers in this area that are tightly linked. So areas really of low recombination, and where basically you see, sometimes you'll see a very constriction of the graph here. You see, this is not a very, you'll see finer constrictions in further graphs that I'm going to show. These are areas of high recombination, essentially. And you can actually see each of these pixels lines up directly to the marker over here on the right. And you actually have your genetic map over here on the right as well. So the area of high recombination, if I slide over to the right, and you can zoom into these, onto your screen without losing too much resolution, which is nice. So you can zoom into this area, you go across, and you see there's more recombination in this area than there is in the area over here with low recombination when I slide over to the markers over here. Okay? So again, this is a nice, if you want to call it 10,000-foot view of your genetic map. The other thing that's nice on the bottom, it shows proportion of A and B alleles. Basically, you're looking at distortion over here or no distortion. So what you want to see is it's an even, you want to see nice even red and blue contributions in the recombinant red line population. So you don't have, so it's your allelic proportion, or you can call it distortion. And so the yellow here is showing there's a little, for all these markers, there's a higher frequency of the A allele, a slightly higher frequency of the A allele than there is the B allele down here, and so on. And in this case, there's a little slightly higher frequency of the B allele than the A allele. So that's what the kind of the lighter blue and the yellows are showing over here. And so actually, this is one part of the graph. If you actually slide to the right, you actually see this next part of it, and you see the actual graphical genotypes. And you can pull these as single images or as images with the previous image. So here's your graphical genotype, which also shows, again, your markers, their order, the genetic distance, and also the allele frequency, just like before, in just like a different graphic. The other thing that you see here, it's not that easy to see in this case. You see gray and white, white little pixels, essentially. The gray pixels mean there's missing data. And what you're seeing over here, there's 4 lines that we chose to leave out of our analyses. So we put them all as missing data. Because there's a number of reasons to do that. Maybe it's just because they have too much missing data, or basically maybe they have too many heterozygotes in this recombinant inbred line population. But we're not comfortable in keeping these lines, 4 lines, in our data set because it's kind of messing up our analyses. And so you can just cancel these guys out. But of course, there's individual missing data points for different markers for different lines. What you're seeing in the blue and the red here are the double crossovers in there. So you want to minimize double crossovers, of course. And here it counts the double crossovers at the bottom. You have 2 rows, but that's just really for display. So this is really line 1, line 2, line 3, and so on. So in this case, line 3 has 4 double crossovers across this linkage group and so on. The X's in this case show that, this guy has a lot of double crossovers. Maybe there's some problems in the markers order in this area. If you go across, these markers actually represent areas of low linkage, and sometimes you basically don't have you may have double crossovers in the order here, but you may not also have the resolution to make that call in the first place. And so you have to balance that, as a scientist to say, are these really a problem, or are these areas that the markers are so tightly linked that we really can't make much, really not sure of what that order is. So I'll give you an example of how we've used that tool in Pepper. So we used our Pepper Affymetrix chip to, again, we mapped about 16,000 different unit genes on this. And this is a genetic map. So Pepper, we mapped them on a interspecific cross where we knew that there's a translocation between chromosome called P1 and chromosome H between the wild type and the cultivated type. So what translocation does, it basically gives you false or pseudo linkage, and this was elegantly actually shown in a Pepper map actually created by Wu et al. Out of the Cornell group a few years ago, 2009. And so they identified this, I'll say, with a relatively, what's the word? This is not an ultra-dense genetic map, but it really captured the translocation nicely. So what you see is a reciprocal translocation where P8 wild, the section over P8 wild over here, is actually translocated to the bottom of chromosome 1 in the cultivated peppers. And at the same time, there's a section of the cultivated PH which is found in chromosome 1 in the wild type. So basically the P8 basically is translocated down here to the wild type. So what that does is give you pseudo-linkage between chromosome 8 and chromosome 1. And we saw this really nicely in check matrix. So basically what check matrix is saying, the markers in this area have pseudo-linkage with the markers in this area. So that's why you see these dark red dashes over here. So this is not what we want to see in our genetic maps. And there's actually a very nice breakpoint here which basically says, you know, this is a big gap. There's a lot of recombination. Here's a probable area where this linkage or the pseudo-linkage exists. So this is basically a mistake. We've put together P8 and P1 together in our genetic map. But we saw this right away. It just glared out to us and said, okay, we need to break these linkage groups. We did checkmate our first round of mapping with check matrix. This is what we found. We've compared all markers. Here's the linkage group I just showed you before. So these, but we got 9 linkage groups. We did this initially with lettuce, and with 9 linkage groups in lettuce, we were ecstatic because that's how many chromosomes are in lettuce. But we have 12 in pepper, so that's a problem. And we found basically 3 areas where there were some logical breakpoints where we have these really fine areas of basically repulsion. If you want to see, you see these blues all over the place. So this was first the P1, PA translocation. And there was 2 areas right here also in linkage group 6 and linkage group 7. And you see this repulsion saying, you know what, the markers over here are really not happy with the guys down here. And so we broke those linkage groups, we refined our map, and this is what we get. We got a really nice map, genetic map. Got our 12 linkage groups, about 2,900 genetic DINs, and actually we're writing up the publication for that right now. But basically what I wanted to show with check matrix is that it's a really nice way to find, you know, to look at your linkage groups, your genetic maps, and really refine them and pinpoint maybe some problems which you have. The other thing that's really nice is that each pixel is connected to a marker. You zoom in and you say, ah, this is a marker that has a problem. I want to go back to here. There's a couple other highlights. You see over here there's this yellow versus everything around here is red except there's a marker here that is yellow. So it kind of belongs here, but for some reason it's not as tightly linked as the other markers. So we can go to this marker and ask the question and look at the data again and say, you know, is this data good? Where does this marker really fit in here? So it's not just the, you know, the glaring breakpoints that it shows. Everywhere there's basically a break in the color, so to speak. You ask the question and go back to the marker order and see if you can refine it. And so we did that, and again, so we've minimized. We don't really have any of these glaring breakpoints in this genetic map, and we're really quite pleased with this genetic order. And we verified this genetic order in join map, and we got basically the same results.